All right, if you've got an electrical machines exam on the horizon, you are in the right place. We're about to tackle one of the absolute bedrock concepts you have to know, the DC motor voltage equation.
So let's start with a question right off the bat. What is the one thing, the single key, that unlocks pretty much any DC motor problem you're going to face? I'm talking starting torque, speed control, all of it.
It all comes down to this equation. Now I know what you're thinking. Great, another formula to memorize. But stick with me, because our goal isn't memorization. It's to get you to feel this thing, to understand it so deeply that you couldn't forget it if you tried. And how are we going to do that? With a super simple but really powerful analogy. We're going to forget about electricity for a minute, and instead I want you to picture something really simple. A water pump, pushing water through some pipes.
So you see it here. On one side, you've got our DC motor circuit, right? It's driven by voltage. On the other side, a simple water pump system driven by pressure. What we're going to do is map every single piece of that electrical equation to a part of this water system. Trust me, by the end of this, that formula is going to feel like total common sense.
Okay, let's get into it. First up, VA, the applied voltage. Easiest way to think about this, it's the total electrical oomph you're getting from your power source. You know, the battery, the plug in the wall, it's the total power you've got to play with. So in our water world, this is super straightforward. VA is just the total pressure the pump is creating. It's the maximum push driving all that water through the pipes. Easy, right? All right, next up is EB, or back EMF. Now, the name here is a little tricky. Back EMF sounds like something bad, right? But it's not a loss at all. It's actually the voltage the motor generates itself just by spinning. This is the part of the voltage that's doing the actual useful work, turning the fan, lifting the weight, whatever the job is. It's the work voltage. And our water system makes this crystal clear. The back EMF, that's the pressure needed to do the job. So let's say our pump is trying to lift water up to a tank on the second floor. EB is the exact amount of pressure it takes to fight gravity and get that water up there. It's the pressure doing the real work. Okay, next piece of the puzzle, IA, the armature current. This one's simple. If voltage is the push or the pressure, then current is the flow. It's just how much electricity is actually moving through the wires. And this lines up perfectly with our water analogy. The armature current is just the flow rate of the water. You know, how many gallons per minute are coursing through those pipes? That's our current. And last but not least, we have RA, the armature resistance. Every wire has it. It's just a natural opposition to the current, kind of like electrical friction. Back in our water system, this is so easy to picture. It's the friction inside the pipes. Maybe the pipes are a little narrow, or they're old and rough on the inside. Whatever it is, it fights against the water flow, and because of that, you lose some pressure. Okay, so here's the key takeaway. When you have that flow, IA, pushing against that friction, RA, you get a voltage drop. That little chunk of the equation, IA times RA, is literally the voltage that gets eaten up just fighting against the motor's own internal friction. In our analogy, it's the pressure that's totally wasted just overcoming the crud in the pipes. So let's put it all together on one screen. This right here, this is your exam cheat sheet. Seriously. VA, applied voltage, that's your total pump pressure. EB, the back EMF, that's the pressure doing the actual work, lifting the water. IA, the current, simple, that's the water flow. And RA, resistance, that's just the pipe friction. See how it all lines up? Okay, now look at the equation again, but think in terms of water. All it's saying is that your total pump pressure has to go somewhere. Part of it is used for the work, lifting the water, and the other part is lost to friction. Total pressure equals work pressure plus lost pressure. It's not a formula anymore, is it? It's just a fact. It's conservation of energy. It has to add up. And this is why this matters so much. This one little equation explains everything. Let's take motor starting, for example. The instant you turn it on, the motor's not spinning, right? So the speed is 0, which means our work voltage, E sub B, is also 0. So the equation just becomes VA equals IA times RA. And since that resistance, RA, is usually a super tiny number, the starting current, IA, has to be huge to make the math work. That's that massive inrush current everyone talks about. Or what about speed control? We know E sub B is tied directly to speed. So if you want to change the speed, all you have to do is play with the balance of the other terms in the equation. It all comes back to this. So I'll leave you with this. A little food for thought for your exam prep. Now that you see this equation as a perfect balance of forces, the total push equals the work push plus the friction loss, how would you mess with that balance on purpose? How could you change things around to make the motor go faster or slower? Think it through. You've got this. Good luck.
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.